Good afternoon, everyone. Thank you very much for joining us for the third series of Materials Things Masterclasses. Today we have Andrew Lawrence sharing his passion for timber, discussing timber's unique properties and the recent technological advances that are helping timber become the standard construction material alongside steel and concrete. Before we start, I have a few points to note. Please type your questions in the chat. Andrew will answer them at the end of his presentation. Please avoid using the raise your hands button. It's just easier if you type your questions in the chat. Please turn off your videos and mute your microphones. And we are recording this session, and we have recorded all other sessions that are now available on our YouTube channel. I'll share the link in the chat so you can check out previous webinars. Well, that is enough from me. Off to you, Andrew. The floor is yours. Thank you very much.
Great. Thank you very much, Bruna. Hopefully that works. Okay. So I thought I would start with this slide. This is some of the tallest timber buildings which have been built across the world in the last 10 years or so. And I think what you can see is that something pretty remarkable is happening. I think probably even 5 years ago, nobody would have guessed that today there would be, I think, 4 timber structures which are about 20 stories high. And people are talking about much taller ones. And so what I thought I would do today is just try and talk about why is that happening, what are the challenges, and what are the opportunities. Now, we're often challenged that, well, surely wood can't last because it rots, doesn't it? And so I'd like to show this. This is, I think, the oldest timber building in Europe. It's a church. It's halfway between London and Cambridge. And if I tell you that this was built just before the Norman invasion, you'll realise that this church is something like 1,000 years old. What you're looking at is the wall of the church is actually oak tree trunks. And the reason that this has survived is that the wood is kept dry. When we talk about rot is a fungus, and a fungus, like any organism, needs water to survive. And so if we keep the wood dry, our timber structures really can last forever. And so what we've got here is we've got an overhanging roof, and then those wooden tree trunks are lifted up off the ground on this brick plinth. What I'd like to suggest is that the real challenge with wood is that it grows in these, shall we say, rather awkward shapes and sizes. And of course, tree trunks are not even cylindrical. They're really sort of conical. And so if we chop those tree trunks into straight lengths, then we'll be cutting sort of tapering pieces off the sides, and that's a huge wastage. And so what we tend to do is we'll tend to cut tree trunks into 5 or 6 meter lengths, so that the diameter is relatively constant over that length. And so that means if you go down to any timber yard today, you'll still find that you cannot buy a piece of timber in any species longer than 5 or 6 meters. Back in the 13th century, if you happen to be a Cistercian monk, you had exactly the same problem. They probably didn't bother you if you were a Cistercian monk. The largest thing you probably wanted to build was one of these barns. Actually, I rather like the idea that this barn was, used for 800 years for its original purpose, as a grain store, and that for me is true sustainability. But the point is that for these smallish structures, those 5 or 6 meter lengths of timber cut from a tree, not a problem. But of course, today we want to build much larger structures. So what do we do? And the real breakthrough was 1930s and into the Second World War, when waterproof glues were developed, and an early use of those waterproof glues was the mosquito. And on the mosquito, of course, was entirely made of wood, That's why it was so fast. It was actually faster and lighter than the Spitfire. On the left, you can see a detail of the wing, and you can see that the wing has got made a tiny little glulam beam there. Of course, if you want to fly through the clouds, having your laminated beams made of waterproof glue is very helpful. But to be honest, it's also helpful for timber in construction. While I've said that timber structure and buildings should be kept dry, of course, it always gets a bit wet during construction. And so having a waterproof glue is really, really important. Now, once we have got a decent glue, then we can take these short lengths of wood, 5 or 6 meters long, cut from the tree. We can cut a finger joint. That's what you can see on the left, that finger joint cutter. We can cut that in one end, and we can join 2 lengths of wood together. And so on the right, you can see this completed glued finger joint. So now we've got much longer planks of wood. We can then take those, we can pass them through a glue curtain. That's raining resin, and it's raining hardener, and the resin and the hardener get mixed on the surface of the wood. And then we clamp those planks of wood together overnight until the glue's cured. And of course, it's pretty easy to curve the planks while the glue's still wet. And so we can make a curved beam, or we can make a straight beam quite easily. Now, by laminating wood, it actually gets us around another difficulty. If we take a trunk of a tree and we chop it up and saw it up into planks, there's a huge variability in strength. Even from the same tree, there might be a variability in strength of perhaps 4 or 5 times. It's pretty obvious why. Wood has knots in it. The knots are the remains of the side branches, and I think you can imagine that those knots if those knots are in the wrong places, for example in the beam, if the knot is in the bottom image, if the knot's at the bottom, that's going to massively reduce the strength of that piece of wood. But of course, chop up the log, randomly glue the pieces back together so the knots don't go all the way through, and we end up with something stronger. And so this is the idea of a glue laminated, a glulam beam. And what we might even do, we might actually put the pieces which have got less knots, smaller knots towards the outside, and the pieces with larger knots in the middle, so that we're using all the resource, but we're putting the stronger pieces in the more efficient locations. And so that's this idea really of glulam, that we can make much larger and much stronger members. And I'll just show you this because this is the largest glulam beam I've ever seen. It was about 40 meters long and 2 meters high, and it is not uncommon to transport timber members of this size across Europe. Now, wood, of course, has always been a big part of the construction market, generally for small houses, rather like this, 1- and 2-story buildings. This is called lightweight timber frame or platform frame construction. It's an incredibly efficient way of building. But of course, it's also relatively weak, and so you wouldn't really want to build in this form of construction more than a very small number of stories. The big change is that we are seeing wood used for much bigger buildings. This is a tower which we are currently building in Amsterdam with Team 5 Architecture. So why is this change suddenly happening? And I would like to suggest that there are 3 reasons. The first is what we see here, computer fabrication. Now, you might say that, well, everybody does computer fabrication. But when Martin Self, as it was, took this photograph in 2005, this was the only computer fabrication in the timber industry. This was a particular factory near Munich, whereas now everybody has one. So that's a really massive change in the last 15 years. And of course, what this does is we can cut out pieces of wood incredibly accurately. Compare the tolerance of a precast concrete panel, which might be plus or minus 10 millimeters, with a machine piece of wood, we're looking at plus or minus 1 millimeter. That enabled us to build this structure with Alvaro Caesar, and in this we had 459 different pieces. I don't think this building could have ever been built before computer fabrication, and I don't think even today it could be done economically in any material other than timber, simply because timber is so quick and easy and cheap to machine. Now, the second invention was cross-laminated timber. Now, you might say, well, cross-laminated timber is not a new thing, and you're right, it was invented well over 20 years ago, but it's only been cheaply available for the last 6 or 7 years. And if you don't know what cross-laminated timber is, I've drawn that sort of image top left, and you can see you simply have a layer of planks, and then you glue another layer of planks on top at 90 degrees, and you carry on doing that until we make these sort of thickish panels, as you can see on the right, with 3, 5, 7 or 9 layers. So a really clever way of making large panels from small trees. And the third invention is these modern screws. You can see one at the top, and you can see it being installed at the bottom. And that screw, it's made of a really high strength steel, so it will self-tap its way into the wood without any pre-drilling. And it will carry, each one of those will carry something like the weight of a car. So again, a pretty recent invention. And so now we have a really strong, quick way of joining 2 pieces of wood together. So if we add together those 3 developments, then we have what you can see on the left, which is this sense that a timber building becomes like a giant piece of flat pack furniture. This was a temporary structure that we did with Alison Brooks called the Smile. It was about 40 meters long, and it was assembled in just 7 days. And so that is really, that's the great advantage of wood is, yes, it's our only renewable material, but the real advantage it has is speed of construction, because it's prefabricated, because it can be cut to really accurate sizes, that giant piece of flat pack furniture image. And not only is it fast to construct with, but it's incredibly quiet. So the Smile that you can see here was actually built in the middle of a university courtyard at the same time as lectures were going on. And I think it's no coincidence that apart from residential buildings, a lot of the buildings that we see being built in wood are schools, and sort of university buildings, and where there's, where actually building something quickly and quietly is really, really important. So now what that speed gives you is that the speed means that suddenly wood can compete on cost, because it is the bare cost of the wooden structure, and that's this sort of red bar on the bottom. What I'm doing here is I'm sort of comparing a typical cost of a typical wooden building on the right and a typical concrete building on the left. And a wooden building, the cost of that bare structure in wood in red is 5, 10, 20, 30% more expensive than the cost of a bare steel or concrete structure. But because the program on site is a lot shorter, it might be up to 30% shorter, therefore there are savings on site. There are labour savings, there's savings in the crane time. And what that means is that the total cost of a timber building is now very similar to the total cost of a steel or concrete building. That is the change which has happened in the last 10 years. And that essentially is why we're seeing more and more timber structures. And so from 2008, 2010 or so, we see buildings very much like this going up all over the world. The one on the left in London, the one on the right in Melbourne, and there are many others as well. These particular ones are residential buildings, and you can see on the right how all the walls and the floors are just made of those large CLT cross-laminated timber panels. Now, I'd like to show you this. This is, you'll notice, is not timber. This is actually precast concrete. But I think this has some useful lessons for today, because in the 1960s, precast concrete was very much in the situation that timber is in today. Just like today, we're getting really excited about wood and we're building bigger and bigger and bigger buildings. So it's exactly what people were doing in the 1960s in precast concrete. Within a few years, it went from 5 stories high to 20, 25 stories. We got to the point where in the UK alone, we had built about 1,000 of these buildings. And then somebody left the gas on in their kitchen. There was a small gas explosion, and that gas explosion led, as you can see here, to the collapse of part of the building. It was probably another 40 years before we built again in precast concrete in the UK. This particular building was called Ronan Point, of course. I think my point here is that actually there's nothing wrong with precast concrete. It was simply that people got very excited about the material, and the buildings almost sort of got ahead of the codes. And I think we're slightly in the same situation today, where we have building codes which were written 30 years ago, when timber buildings were quite small, and yet we're building bigger and bigger timber structures. And so this is just me raising a little warning flag, saying timber's a great material, it has huge potential, but remember, for these bigger structures, we're still very much in the research phase. If I show you this, you might remember this one. This was the ice rink in Germany, which suddenly collapsed in 2006 on top of quite a lot of children. Now, this structure, of course, is wood. And I think what's of interest to me is not so much the reasons for the collapse of this particular wooden roof, but is that after this collapse, or I believe all the wooden roofs in Germany were checked, and problems were found with, I think, about 100 of them. And it's just to say that timber's no different from any other material. In any new form of construction, it takes time for safe methods of design to be developed. And just because people have built much bigger structures doesn't mean they've actually been well designed, because as engineers, when we design, we're designing for really, really extreme events. As here in Germany, it tends to be Central Europe. It tends to be snow, which governs. In Japan, it tends to be earthquakes, and in the UK, it tends to be wind. It's just this little sort of warning flag, and that remember that by building bigger timber structures, we are going beyond today's current codes. And so part of what I wanted to say today was how can we design safely in timber, recognizing the fact that it's, for these bigger structures, it's still very much in the research phase. Now, I think the first step is to remember that wood is a very different material. So, if you think about the trunk of a tree, the function of the trunk of a tree is not to be turned into buildings. The function of the trunk of a tree is to get water from the ground up to the leaves. And so we can imagine a trunk of a tree like a bundle of drinking straws. If you look at that microscopic image in the bottom middle, it does indeed look just like a bundle of straws. And if you think about a bundle of straws, it's really strong parallel to the bundle. You can squash it or you can stretch it, but across the width of a bundle, it's quite weak. You can pull those straws apart quite easily. You can squash them quite easily. And so that is the model of wood that I want you to hold in your mind. It's a material which is anisotropic. It's about 5 or 10 times stronger in one direction than the other. Very, very different from the sort of steel or concrete material that we're normally used to working with. One implication of that means that wood is quite brittle. So this is a connection which I watched being tested in the Technical University of Munich. And I was standing there with my video camera watching this, and there's a steel connection on the right and timber on the left, and the two were being pulled apart. And I was watching with the video camera, and nothing happened at all. It was very boring. And then suddenly it went bang. And there was absolutely no warning of failure. And that's what I mean about wood being a brittle fibrous material. Very, very different from steel that we're used to working with, which is much more ductile. So very much when we say wood's brittle compared to ductile steel, it's very much a difference between how a matchstick snaps and a paper clip will just bend, and you can keep bending it back and forth. Now, another implication of wood being a fibrous material like a bundle of drinking straws is that it is incredibly efficient. Weight for weight is about 4 times better than concrete. That's good. Means we can have cheaper foundations. It means there are about 6 times less lorry deliveries to site compared to concrete lorries. But of course, it does mean that a wooden floor is quite lightweight compared to a concrete floor, and therefore it's much more prone to vibration. So this is us doing some vibration tests on a particular wooden floor in West London. And because what we're trying to do is we're trying to make sure that we can accurately predict the performance so that the finished building is okay, so that nobody complains, and very much the results from testing like this we have been feeding back into the new European building code for timber buildings. That code will come out in about 2 years' time, and I think you can be confident that when buildings are designed to that new code, incorporating all of this latest research, that those wooden floors will have a very predictable performance by calculation, and we can make sure, because we don't want problems in our buildings, we want to make sure they're okay, and so we can make sure that those buildings are okay. Now, probably the final and biggest implication of wood being a natural material is, of course, that it burns. And not only does it burn, but of course it can carry on burning potentially until the building collapses. So this was us doing our own test on a small CLT fire compartment, a small CLT room, and we set light to, there was some fuel in the middle of the room, we set light to that so that then the CLT walls and ceiling caught fire. And what we wanted to do was try and understand the conditions for self-extinguishment. If we covered over more and more and more of those CLT surfaces until in the end we just left the ceiling exposed, could that ceiling carry on burning by itself, or would it self-extinguish? Now, if we're building a relatively small, designing a relatively small timber building like this one, this happens to be a 4-story office that we built for Sky. I think you can imagine that a 4-story office building from a fire safety point of view is comparatively low risk. The fire brigade can stand on the ground with their hoses fighting the fire from the outside. Nobody's asleep because it's an office building, or hopefully they're not asleep, and so everybody's awake, so when the fire alarm goes off, everybody can get out of the building fast. So this is a relatively low risk building. So if this if there's a major fire in this building, even if this building were to burn to the ground, it's very unlikely to be a life safety issue. But compare this sort of structure, the one that's this one that we're building in Amsterdam, 20 stories residential building. So people are going to be asleep, there are going to be elderly people, there might be children. There's no way the fire brigade can fight the fire all from ground level. The fire brigade are going to have to go into the building to fight the fire, and go into the building to make sure that everybody's got out. And of course there are other buildings close around as well. I think you can imagine that if this building was to catch fire and carry on burning and maybe burn to the ground, that really wouldn't be very good news. And so we need to, because wood's a combustible material, there are ways to design this safely in fire, and I'll talk about that a little bit later on. But the point is that we need to rethink how we design buildings. That's the point I'm trying to make. Wood is a different material with different characteristics. We can't just do what we normally do for steel or concrete buildings and apply it to wood. And just to give a few examples, this is the Metz Pompidou, which we built together with Chugurubin in France. This was actually a statement that Chuguru made. The design might look quite complicated, but it's really very simple. And absolutely, the architectural design was beautifully simple. This idea of a roof which provides the weather protection to the art galleries underneath. But from a structural engineering point of view, this structure was an awful lot more complicated. You can see here in this image, this is our computer model and shows you the sort of stresses that were going on. But what we found in our computer model was, if we played with some of the support conditions, if we played with some of the assumptions in the model, then the distribution of forces within that roof structure would vary. And I think you can imagine that in some places it's trying to work like a dome, like a compression dome, like an arch. In other places it's trying to hang rather like a cable in tension, and in other places it's relatively flat and it's working like a beam in bending. And because wood's a brittle material and we didn't want to break it accidentally by mistake anywhere, so we had to explore all those different load paths. It took us well over a year to explore all the different load paths to make sure we had a structure which would be safe. What we also did, this is the connection between the layers. What you're looking at is a giant wooden bolt on the left there. That wooden bolt is about 8 or 9 centimeters diameter. But of course, as you drag that bolt sideways, it could split its way out of the wood. The wood could split, just like those drinking straws, the straws can split apart. And that would be quite a brittle behavior. So we wanted a more ductile behavior, a more plastic behavior. And so we put in those red dotted lines represent screws. The idea to reduce the risk of splitting to get a more ductile behavior out of the structure. Now, as I say, on Metz, we spent well over a year on the design, but that was a very special building, and I think that merits special attention. But on on most buildings, none of us have the time or the money to spend that long, and so we really need to design our buildings in such a way that they suit the material. And I think this one's a very good example. This is now the largest timber roof in the UK. It's absolutely huge. It's about 33,000 square meters. Each of those square sort of black line demarcated roof panels is about 15 by 15 meters. Brilliant design by Cullinans. Now, of course, what this roof looks like is a two-way spanning grillage. And indeed, if we were doing this in steel or in concrete, it would indeed be a two-way spanning grillage with rigid moment connections at each node point. But in fact, in timber, the different material, we need to do things in different ways. And the way to do things in timber is to design it as a one-way spanning structure. So that's what you're looking at here, is one-way spanning beams with short infill pieces. Now, as a one-way spanning structure, that means we know exactly where the load's going. And so we can make sure that we know where the load's going. We can confidently design all the members, design all the connections, make sure that none of those connections fail in a sort of brittle way. And I think as engineers, we often rely on architects to push us to sort of do new things and innovate. I do often think that if it was just left to engineers, every building would look like a two-story shoebox. Now, in this case, we work with some wonderful architects in Amsterdam called Team 5 Architecture, and Team 5 said they wanted to build the tallest wooden building in the world. And so we said, well, what is a good way to build in timber? It's a different material. What's a sensible way to build? And now, if you look at many timber residential buildings, you can tell they're timber buildings because the outside walls of the building are wood, and then there are small punched timber windows. And the reason there are just small punched timber windows is that the whole outside wall is being used as the structure of the building, shear wall, or if it's a tall building, perhaps you can imagine it like a big timber tube. But we didn't want that. We really wanted to free up the facade so that we could get these fully glazed facades you can see here. And the other thing we wanted a flexible structure. We didn't want like those early CLT buildings where all the walls in the building are structural, all the walls are therefore fixed, you can't move them, you can't adapt the building in the future. We wanted a building which would be truly flexible, truly sustainable, so that it would still be being used in 100, 200 years time. This idea that so we want to make it flexible. We didn't want every single wall in the building to be a structural wall. We concentrated that CLT, that timber structure, into the party walls between the apartments. That's these thick black lines you can see here. And then all the internal partitions inside the apartments, we just made those as movable, lightweight, non-structural timber partitions. Now, because we're going up to 20 stories, we want those walls to be really, really stiff. Now, the normal way of making a CLT building is what we see on the right, what we call a platform frame, wall, floor, wall, floor. But of course, those walls are squashing the floors. And I've told you that wood is 5 or 10 times weaker across the grain. And so those walls will not be very stiff, and that whole wall is going to shorten a little bit. But it wasn't going to work on the 20-story building. And so what you can see on the left, what we've done is there's actually we're not squashing the floor in between the wall panels. Actually, the wall, there's a little concrete plug there, and the wall above is directly sitting on the wall below. And that gives us something else as well, because the floor panel is not continuous across the wall. The floor stops and starts, and that means that vibration cannot get transmitted from one apartment to the next apartment next door. So all these things about, how do we design differently in wood? And the final thing is you can see that we've only exposed the ceiling of that room. There's only one exposed CRT surface. And that's this idea that we're trying to encourage the wood to self-extinguish in a fire scenario. So this building is safe in a passive way, no reliance on sprinklers, that the wood will simply self-extinguish and will be sort of life safe. Now, those walls I showed you, of course, they're quite thick. I think they're 200 or 300 millimeters thick. So you can imagine they're almost a little bit like concrete shear walls. But of course, different from concrete, they are made of lots of small pieces. And however hard you try, you'll always get very small movements between those small pieces, sliding a little bit, opening and closing of joints. And so those CRT shear walls will never be as stiff as a concrete shear wall. And in fact, at 20 stories, we simply could not make this building stiff enough. It would have just been too uncomfortable for people under wind loading. And so what we did was we incorporated a concrete core. That's that red line there. And, you know, I have no problem mixing and matching materials. I think all the construction materials, steel, concrete, timber, all have advantages in different scenarios. So why not mix wood with other materials? And so that brings me on to the next slide, really, which is, you know, what's my prediction of what we will be building in wood in 10 years from now? You know, I said at the moment, we're very much in this research phase. If you look at it in the press, everybody's saying that we should be building 40, 60, 70-story timber skyscrapers. Of course, it's complete nonsense. It simply would not work from a structural point of view. What I think we can do is on these taller buildings, perhaps above 10 or 12 stories, what we can do is we can mix wood with other materials, such as top right there. We could have a steel frame with CLT, timber floor slabs. So again, the whole thing prefabricated, dry, really fast construction. Alternatively, we could have what we call a timber concrete composite panels. That's what you see bottom right, perhaps a 10 centimeter thick precast concrete on glulam beams. So you'll get that to span about 10 meters or so. So, you know, you compare that to solid concrete, which might have been 25, 30 centimeters thick. So we've sort of halved the amount of concrete in the floor in the building, and so we've reduced the carbon footprint of the building. So, you know, using each material to its advantage. But I think really for the stability structure, lateral stability structure, for the core, for the vertical structure, you know, it makes a lot more sense to use a stronger material like steel or concrete for those elements, stronger, stiffer material. But think about incorporating wood in the floors, and what that does is it not only reduces the carbon footprint of the building because there's less concrete in the floors, but what you're also doing is you're reducing the weight on the columns, and so you can get away with smaller columns, and so there are further carbon savings in those areas. Now, I think in 10 years' time, we will also continue to see residential buildings up to about 10 stories high. Now, why 10 stories high? Well, 10 stories is roughly the sort of height where you will be able to make an entirely wooden building, where those wooden walls, where there are lots of small pieces of CRT, will be just about stiff enough to stabilize that building under wind loading. Now, you might never know these buildings are made of wood because this is a residential building, so it's got very tight fire requirements. It's got very tight acoustic requirements. So most or all of that wood is going to be covered over with plasterboard, with fireboard. But the wood is still a really good method of construction, really fast way of building. And I think the third type of timber structure which we'll be seeing in 10 years' time will be these sorts of buildings, roofs and low-rise schools and offices, 3-4 stories, that sort of thing. The point about these sorts of structures is that there are much lower acoustic requirements, and there are much lower fire requirements in most building codes across the world, because people are not asleep, because it's a lower rise building, because people can escape from the building relatively fast. And what all of that means is that the wood can generally be left exposed, visually exposed, as you see on the left. And so that, of course, saves on the time and cost of adding on finishes. And also you see this wonderful beauty of the wood. And I think that brings me on to my penultimate slide, which is just to make the point that a successful timber structure doesn't only need a good engineer, it needs an architect who really understands the material. And this was an experimental structure which we built with DRMM. And the challenge here was to build the world's first hardwood CLT structure. And the point about exposed timber structures like this is that the structure is the architecture and the architecture is the structure. So you can really see how important it is for not only engineer but also architect to really understand the material. And that's even more important when it comes to waterproofing, which usually is the architect's responsibility. You know, you cannot waterproof a timber building in the same way as a concrete building. I'm fed up with the number of times I'm seeing people thinking that a flat CLT roof can just be waterproofed like a flat concrete roof. It's a different material. It's much more vulnerable to water ingress, and we need to think about that. Think about the risk of leaks in the future, and guard against it. And I think the what I always say is have two lines of defence against water ingress. You know, always think whatever your first line of defence against water is, it's always going to fail at some stage in its life. When it fails, what's going to happen? Because we can't afford to let water get to the wood. So think about two lines of defence, because remember what I said on the very second slide. If we can keep the wood dry, it really can last forever. And so just to finish, I really do think that there's a huge potential to use more wood in construction. It's not a replacement for steel and concrete, but it does have advantages in certain circumstances. And I think more and more we're starting to see it as a standard material alongside steel and concrete, and maybe even mixed together with them, using all the materials to their best advantage. But we, as we go through over the next 5 to 10 years, as we continue to go through this really exciting research phase, building bigger and bigger timber structures, we just need to remember that we are in a research phase still. We're very much where precast concrete was in the 1960s, where reinforced concrete was in the 1930s. We're in a research phase. Don't be too arrogant. Ask questions, speak to people who've been there before, who really know what they're doing. Remember, this is well beyond what the current building design codes and building regulations were designed for. So you have to go back to first principles. And if we do that, then we can design safe, successful buildings and really show what timber's capable of as this amazing construction material. So thank you very much indeed.
Thank you very much, Andrew, for the amazing presentation. It's so nice to see someone so inspired by their job and such a fascinating topic. So I'll start with the questions. So the first question is from Patrick from the LA office. So he's asking whether the vibration testing was for European codes for traditional wooden floors, or if it was for CLT floors.
Good question. So most of the recent testing which has been done is for CLT floors. Because that is where, I mean, to be fair, a lightweight timber cassette floor with joists and OSB or plywood is very, very lightweight, but it's also fairly low strength, so you don't really consider using that in a single family house. I wouldn't really consider using that in a multi-occupancy dwelling. I mean, you can, but you won't get terribly good performance. I always rather quote the Germans. The Germans refer to British domestic floors as trampolines. And actually that's absolutely fine in a single family house. But I think if we're talking about multi-occupancy buildings, blocks of apartments, if we're talking about offices, schools, we need much better performance, and for that we'd always be using CLT because it's a much stronger, stiffer material. That's where all the recent research has been. There is now agreement across Europe for the accurate vibration dynamic design of these sort of CLT floors. I think there is talk of following a similar basis in the States as well. And so we do know, the research is there. We do know how to design wooden floors so that they perform well from a vibration point of view. There have been a few problems in the past, but that was due to poor design rather than any specific problem with the material. But the real way to make sure that everything's okay is to get the stuff into the building codes so that nobody has any choice but to follow it. That's what we're doing. The new Eurocode that comes out in 2 years' time will be very, very robust, and there shouldn't be any more problems after that.
Very exciting. So the next question is from Caroline, is how are the timber high-rise structural elements tied together for robustness purposes?
Yeah, that's a good question. So I'm not sure if everyone on the call knows, but robustness is often referred to as disproportionate collapse. It's a UK concept because it followed on from Roland Point with that precast concrete building in the 1960s that I showed you. After that, when there was the explosion in somebody's kitchen and half the building collapsed. So then this concept of disproportionate collapse was developed, starting in the UK. And subsequently now applied over much of the world. And it's this idea that if there's a small event, a small accident in one part of the building, you don't want that to lead to a disproportionate collapse of a larger part of the structure. Now there are there are various ways of dealing with that. But to make it work in wood, we need to recognise that wood is a brittle material, and so the sort of catenary action which we often rely on for steel structures, this idea that if you take out a steel column, the rest of the steel floor, steel beams can sort of hang there like a giant cable net. That works for a ductile material like steel, doesn't work for a brittle material. I mean, to be honest, it doesn't work terribly well for concrete either. It certainly doesn't work for timber. And so we can't use that sort of tying approach at all. And that certainly is one of the mistakes that we're seeing being done at the moment in some of these bigger timber structures where people are relying on tying, which is complete nonsense in timber. I think the Finnish are the most advanced in this in Finland, and that they realised some years ago that for a timber structure you really need to rely on element removal. What that means is that you design your structure to make sure that you can remove one wall element or one column and the rest of the structure stays standing. And the way you can do that is by having your, for example, your CLT floor panels spanning multiple bays, so that even if you take one support out, that panel might deflect a bit, but it won't completely collapse. So for engineers on the call, then for robustness of a timber structure, we should be following an element removal approach. And again, this is something else, which isn't yet in the codes, but will be in the codes in a few years' time.
Great. So we've got a question from Daniel on the CLT course and looking to reduce embodied carbon further. So do you envisage opportunities to innovate connections that improve stiffness and reduce slip to maybe make 10, 15-story buildings viable with timber stability?
I mean, it's not impossible. I think we could probably do it now. It's just that it will end up being really, really, really expensive. And because even then the CLT will be less stiff, so you'll end up with very, very long CLT walls, which can disrupt the planning, which can start getting quite expensive. I really would encourage people, because if we might be able to do things technically, but then they just get expensive, and then that gives the material a bad name because it's too expensive. I really believe that we need to make sure that our timber structures can compete. And the way to do that is to understand what types of building it can compete with. And if it can't compete, then to think about mixing it with other materials. And hence this idea, if you look at any of the nearly all the taller timber structures which have been built across the world, say the recent one, Brock Commons, that Fast and Ep have done in Vancouver, or the Ho building in Vienna, they've all got, or as I say, Hout, which we're currently building in Amsterdam, they've all got concrete cores. There is one which is built entirely in timber, and that is the, I think, 19-story building. It's a hotel in Norway, but if you look at that, you'll realise that that is essentially an external tube. It's got trussing, diagonal bracing in the external walls. Not impossible, but it's very, very rarely that will work architecturally.
Very interesting. So the next question is from Andrew. So when talking about wood being used in buildings with mixed materials, do you see much of an uptake of natural fiber reinforced plastics like flax, jute, sisal? Is this almost what glulam CLT is?
Yes, I mean, there's lots of research going on about taking making natural fibers and mixing them with natural resins and making sort of natural composites. But yes, as you say, I mean, wood itself is a natural fiber composite material where you've got cellulose fibers joined together with a lignin glue. And the point about wood is it grows, really cheaply and fast with free solar energy. So that there's, while you can make man-made fiber, while you can make fiber composites, and we could maybe eventually make ones out of natural fiber and natural resins, and that could be really useful for some smaller sort of manufactured type products. I think for something on the large scale, I would simply say, why don't we just use wood? It's obviously going to be cheaper because it hasn't got all that manufacturing that's gone into it.
So the next question is very interesting. So what is your experience in implementing timber buildings in emerging markets, for example, parts of Africa? So this is something I'm particularly interested in finding out, Andrew.
Yeah, no, I think there is huge potential. But it would be a very different form of construction from what I've been showing, because first of all, one would want to be using locally sourced materials, number one. So, making a laminated member, glulam or CLT, is a highly complex, workmanship dependent process that you need to do in a very automated factory. If one wants to use natural cellulose-based materials in developing countries, we want to use the material that's naturally available there. And so we would be looking at locally grown timbers, and very often there's also bamboo available. Bamboo grows particularly fast. We'd be, say, not laminating it, we would be using those materials. I think they should be used in their raw form. So be cutting wood straight from the tree and using it while it's still wet or green in balks, or using the bamboo still in its round, calm form, which is a really strong, efficient form. We need to make sure of two things. We need to make sure that first of all, the material is sustainably sourced. I think that's relatively easy with bamboo because it grows so fast, and plantations are fairly easy to make. With sort of local timbers, in developing countries, and what we're really talking about is tropical timbers. We just need to make sure that those timbers are being sustainably grown, sustainably sourced, because of course there is lots of illegal logging in those countries and lots of clearance of forests to make more farmland. So we need to be a little bit careful about the source of the timber. And the other thing we need to be a bit careful about is that, whereas I gave the simple story at the start when I said that if you keep wood dry, it can last forever, in a hot tropical climate, there are also insects, beetle, termites, which can eat the wood, and we need to protect against those. And the best way to protect against those is with artificial preservatives, which can be sort of pressure impregnated. And so certainly if one's using bamboo, we would always in those climates advocate treating that bamboo. It can be done very simply normally would be done with boron. You can simply put the bamboo culms in a bath of boron, so it doesn't need any complex machinery at all. And the great thing about boron is that it's water soluble, so it will sort of migrate its way through the bamboo, so you get full treatment of the whole bamboo wall, and so it's got full protection against attack from insects and attack from termites. But the other thing about boron is although it's a toxin to insects, it's not a toxin to humans, which is always good. But the thing about boron is it is water soluble, and so you're using it there for protection against insects, but you really want to keep the wood under cover out of the rain, so that the boron doesn't get washed out. But as I say, anyway, you should be keeping wood or bamboo under cover and out of the rain anyway to give it a long life. But you can treat it with preservatives in those sorts of climates to help against insects.
It kind of links nicely to the next question. So are there sufficient quantities of responsibly sourced certified CLT in the market to encourage such transition to the way of designing and building? So I guess this question relates both to the emerging markets and developed countries in that sense.
Yes, yeah, no, that's a fair question. yes, I mean at the moment there are. If I say that despite all the timber that's currently being used for, or the increased timber that's being used in construction, the size certainly of European forests is still growing. In other words, the trees are growing faster than we can chop them down. So there is 80% of CLT comes from Central Europe, Scandinavia, and we have immense supplies of sustainably grown wood. Or to be honest, there've been tight forestry laws in most European countries for centuries, long before there was talk of sustainability or sustainable certification schemes like PEFC or FSC. It was countries just realised it was in their interests to, keep the forests and not completely chop them down, and therefore you chop your forest down as a sustainable rate. In terms of CLT, a lot more. There's nobody knows quite the exact volumes, but there's at least 1 million cubic meters being made every year now. As I say, most of that being made in Europe. The capacity has significantly increased in the last 2 or 3 years, and can continue to do so as required. So it's hard to see any restraints from that point of view over the next few years. And of course, at the same time, we're using less and less wood material for pulp and paper. I think it's a much better use to turn the wood into a building which is going to be there for 100, 200 years, rather than paper or cardboard that's going to be thrown away pretty quickly. So, but no, there's at the moment there's certainly no shortage of supply.
That's very good to know, and couldn't agree more with you on that. So this is a question that's probably in everyone's mind. Is there a date in mind for the updated Eurocode?
Good question. It's not in my hands, but I know from the drafts of most of the code are very close to being completed. I think it's fair to say that certainly for the timber Eurocode, because all the Eurocodes are being updated, but for the timber Eurocode, I think the drafts will be in place by the end of this year, and I think some parts are already being circulated for sort of national comment, should we say, amongst different countries. I think you can imagine that because every country within Europe has to ratify the changes, that can take time. And I think the latest expectation is probably towards the end of 2022 that code will be out. But as I say, a lot of the research has already been done.
Good to know. So the next question is regarding the restrictions of use of timber for buildings above 18 meters in the UK due to fire performance. So is there any future for timber high-rise in the UK?
So, well, first of all, I think it's important to understand the restriction which has been brought in, and the restriction is specifically for external walls. Because of obvious concern about fire spread up the external wall, and therefore avoiding combustible material in the external wall. Now, I'm not sure if personally, I'm not sure if I actually agree with the ban, but I think we can all agree that buildings need to be fire safe, and I think we can all agree that if there's going to be something combustible in the external wall, one would need to take huge care over the design of that and encapsulation and all of that. But as I say, the specific, as I understand, the specific ban is material within the external wall. There is nothing to stop it being used for internal walls. And in fact, if you think back to the Hout building in Amsterdam I showed, in fact, we didn't have any timber in the external walls at all, and that was driven for completely different reasons. That was very much driven by wanting to free up the facades. So in theory, there is no restriction to timber buildings, residential, but that's the other thing, is the regulations are specific for residential buildings because that's where the higher risk, the sleep risk is. In practice, of course, the very fact that regulation exists makes clients a little bit nervous and insurers a little bit nervous, and so it is sadly having a wider impact. but I would like to hope that within a small number of years we would get to a point where there are tried and tested ways of using timber safely in the external wall with appropriate fire treatment, and that there are appropriate tests in place to prove that that construction is okay. So I think it's I think what we're in the moment is a slight short-term thing, which is very much a thing in the UK. But as I say, it is very specific to residential buildings, and if you look at the letter of the regulations, they only apply to the external wall. So there is nothing, with careful fire engineering design, there is nothing to stop us continuing to use wood for the rest of the structure.
That's perfect, good to know. So I think that's all the questions we have. So thank you very much, Andrew, for the fascinating presentation. It was incredibly interesting. Thank you very much for everyone for attending. Just a bit of a plug for the next series of webinars that are coming up. So do sign up in the Eventbrite page. And that's it from me. So thank you very much, everyone.